Right, so it's my pleasure to welcome our next speaker, Elizabeth Polgreen from the University of Edinburgh. Elizabeth, her work and interests are in formal program synthesis and informal verification, and especially the intersection of these two. And she's done lots of really nice work on using synthesis to scale up and make verification more effective. And in particular, I should say Elizabeth is at the forefront of trying to understand at a deep level how LLM-based synthesis interacts with other more symbolic approaches to synthesis. So it's my great pleasure to have Elizabeth speak here.
Thank you for the very flattering introduction. So I've titled this language model enabled synthesis, and I'm going to specifically talk about program lifting, but the things I'm discussing are applicable to other categories of program synthesis. So I think Guy had a very similar slide, but mine is slightly less good because it doesn't have Shrek on it. So language models are great at writing code with some caveats. So if you're writing in a popular language, if you don't mind the odd mistake here and there, you're willing to correct it yourself. And also if you've got a lot of money to spend on it. So, I mean, they're great, but I don't think they've solved the program synthesis problems that I care about. Formal program synthesis, so the world of sort of syntax-guided synthesis, counterexample guided inductive synthesis. This is also pretty good at writing code if the solutions that you want are quite short, and also if you're willing to provide some heuristics. And this usually means like providing a grammar, providing the syntax guidance. It can be other heuristics. But yeah, great under some circumstances, great under some other circumstances. Neither of these are giving us the perfect solution. So what if we could combine them? The obvious question. So what I'm going to talk about is I'm going to talk about in two methods for combining formal program synthesis with large language models. But first, I'm going to give a bit of a background of the class of problems I care about. So program lifting is a specific class of program synthesis problems. So in program synthesis, what we usually mean is we're looking for a function, some function P, such that for all the possible inputs to P, some logical specification holds true. And this specification is usually a first order formula. Program lifting is saying, so we've taken the logical formula specification we have for program lifting is, can we find a function H that is in some kind of higher level language such that it behaves exactly the same as some function L that is in a lower level language, and we have access to L. But broadly, it's a program synthesis problem. And I was going to try and tell you why you should care about program lifting. I mean, in the interest of time, we could all just assume we're motivated. Are we motivated? Reasonably motivated. Okay, cool. Then I won't try and convince you. I will tell you that it is becoming increasingly relevant as you get more hardware that is increasingly specialized, which means you get more. You want to write more of your code in high-level DSLs that apply to specific bits of hardware. So the reason I got into program lifting and started caring about it is because I moved to Edinburgh and I started talking to some of the folks in the compilers group in Edinburgh, and program synthesis just seemed to fit for a lot of the problems they were encountering. So the problem basically is that they want to lift code from a lower language into a new high-level language, and they want to be able to do this without doing it manually. An example that we have been caring about a lot recently is machine learning code, which is so machine learning workflows are dominated by tensor code, and the key to tensor code, to running your machine learning code efficiently, is to write your code, is to have highly parallelized dense algebra. And the easiest way to do that, unless you particularly like writing highly optimized C code yourself, is to write your code in a DSL like Taco, which will then compile down to something super efficient. Not so easy if you have already written your code in C and you now want it to be in Taco, though. So that's where we want program lifting to do the work for us. It's not just Taco. There's a bunch of other stuff that you might want to lift. So there's other machine learning DSLs. You might want to lift between different layers of MLIR. So Alvin, who many of you from Berkeley will know, did some of the original lifting work, lifting C++ into Halide. To give you an example of the type of problem that we care about, so this C function down here is doing the dot product between a row of one matrix and a vector of another matrix. This is what we actually want in einsum notation, which we can then turn into Taco and compile down into something super efficient. Because this is a program synthesis problem, there are many people that have applied program synthesis to these lifting problems. And this has the same caveats as I said for general program synthesis. It mostly works when the solutions you want are quite short and when you are willing to give a carefully constructed grammar. It mostly works. Yeah, question.
So yeah, I'm wondering about how you verify the program at the end, because if you start from a C program, like, do you assume that it's in some restricted subset where you can model its semantics, or like how do you prove that whatever program you get is equivalent to the original?
So different people have done different things. So Alvin's work on verified lifting, he has an encoding of the semantics of the target language into an IR. That means that he can do the verification on this IR because they know the semantics of the target and the source language, so the low and the high level language. In the case of things like C and Taco, Taco actually compiles down into C, so you can map the two C programs. But
you need like invariance to prove equivalence, right?
Yes. So if you want full equivalence, you need to come up with some invariance. Just to give you a spoiler, I'm not going to give you full equivalence, although we are now starting to do unbounded proof, but that means we have to come up with invariance. Alvin's work generates the invariance along with the code.
Okay, thanks.
Yeah. But yeah, so I'm going to tell you 2 ways we can combine program synthesis and LLMs specifically for this application of lifting. Broadly, our idea is that when LLMs make incorrect guesses, they're often in the right neighborhood of the actual solution. This is our hypothesis. This is what we've based these ideas on. And we want to find some way of searching this neighborhood. So I'm going to give you 2 ways of potentially searching that neighborhood around some incorrect guesses. So the first thing I'm going to talk about is, so this is a PLDI paper this year. So we've called this STAG because I love a tenuous acronym, but broadly what we do is we express this neighborhood as a probabilistic grammar, and then we use this probabilistic grammar to guide a classic program synthesis tool with some feedback, and do sort of a classic CGIS style approach. But I'm going to give you a few more details on that. But essentially the idea is we can have a probability distribution over this neighborhood, and we can then search this neighborhood with our classic synthesis methods. So I'm going to tell you that most synthesis is searching so your classic program synthesis is searching a grammar that is usually a context-free grammar. For simplicity, we have chosen to use a context-free grammar to try to represent this space, and we are then placing probabilities over the production rules in this context-free grammar. Now, we want these probabilities to represent what we think it is the language model thinks is the neighborhood. I am doing an approximation of that probability distribution because the language model's actual probability distribution is simply won't work for program synthesis, because I need to have a context-free grammar. And what the language model effectively has is it has a distribution over likely next tokens, given the history of tokens that it spat out. So somewhat of a gross approximation. Another point worth noting is that the grammar for these TACO expressions, or these einsum expressions, is practically too large for us to search with straight up enumeration. And so one of the things we want to do is we want to try and capture the space of solutions that the language model believes might be correct with templates rather than with just a pure grammar. So the first thing that we do is we turn our grammar for expressions into a grammar for template expressions, which means that for everything that is a tensor variable or everything that is a constant, we'll replace that with a whole. What we then want to do is, so we ask the language model for a number of solutions. I believe this number is approximately, I think we tried a few different values. I think we went with sort of, it's tens rather than hundreds, basically, because you start to lose any variation after you've got through to tens. So we collect a bunch of solutions. We then standardize these so that we then have a template grammar that can represent all of these solutions. And then we estimate the probabilities on the production rules very crudely by counting the number of times each production rule is used when generating these solutions. And that, in this example, so this gives you an example of how we might standardize these. So we basically put replace all of the tensor symbols with these constant values. Yes.
Are you standardizing all of them, or each solution gets a template?
Each solution. So we standardize in that we make sure all of the tensor variables appear in a, so every tensor variable is replaced with a symbolic tensor, and every constant is replaced with a symbolic constant, and every index is replaced with a symbolic index variable, and then we make sure they always appear in the same order. So that means if you have A plus B and B plus A, we will turn them both into T1 plus T2, but we will have a set of templates that represents all of the solutions. Yeah.
So these correct solutions are in a DSL, right? So I'm wondering how your experience with getting LLMs to write correct code in that DSL.
It wasn't great. So the DSL isn't. We had to any solutions that don't fit the DSL at all are discarded. We had a couple of fixes that we implemented by default. So things like you've got the wrong type of parentheses, we will fix automatically. And things like you have produced, some reason it can't decide whether it wants colon equals or equals. So we've got a few minor fixes, but we discard things that don't fit.
Okay. And is this black box prompting based approaches?
Yes.
Okay.
Yeah, which is why we're not trying to extract the actual distribution. Yeah. So once we have these standard templates, we can then parse these in with our grammar and count the number of times each production rule is used, and then that gives us a crude probability distribution over the production rules. Given a grammar with some probabilities on, we then want to search this space of the grammar, which, not entirely sure why there were two copies of that slide there, which we do using a star search weighted by the probabilities. This isn't mine. There's a paper, there's a synthesizer called Euphony. We have taken the A star search that Euphony uses. Yes.
What's dimensional analysis? Because that seems to be an input to the search.
Yeah, so the one thing, this also comes back to things that it gives you that are incorrect. So the one thing the LLM is really not very good at is picking the dimensions of the left-hand side of the expression, so the dimensions of the output, and it turns out we can just do that with static analysis. So the dimensional analysis just tells you what the type of the output is, basically. Yeah. Turns out that that's not very easy to predict from the C code if you're an LLM. Yeah, so we can search a weighted grammar with a star. This isn't a new idea. This is just an adaptation from the euphony paper. So we store a queue of partial programs, which we start with the start symbol in the grammar. We pop the partial program from the queue that has the best score. The score is a function of the weights on the production rules you use to get to this partial program, and the probability, like the weights on the likely completion of this program. Which was on the next slide. So we keep repeating this. We keep popping off the best partial program from the queue, and then expanding it with the production rules that are applicable, and then putting it back in the queue with the new scores. And we keep doing this until we've got some complete program. And when we have a complete program, we then give it to we then return to our synthesis loop, which is then when we come to verifying our solutions. Bearing in mind we are enumerating templates here, so these aren't actually concrete solutions at this point. This isn't very sophisticated. The first thing we do is we instantiate all possible completions of the template, and we compile and execute on a bunch of randomly sampled input-output examples. Because of the nature of tensor code, it is actually I don't think we had any cases where something failed the input-output checks and then didn't pass verification, just because of the nature of the tensor code, and our random input-output generation is biased to avoid things like giving us a full matrix of zeros. We then compile and test it. If we find an instantiation that passes the tests, we then verify with CBMC. This is a hard problem. CBMC is only doing bounded verification. It is particularly a hard problem because this is C code with C data types in it. So one of the problems here is that you're having to deal with floating points. And so for a couple of our benchmarks, we found that the floating point verification took so long that we are forced to verify with reals rather than floating points. Yeah, but otherwise we just use off-the-shelf CBMC. And then hopefully we have a TACO program, which it works. Yeah, so we can lift more benchmarks than classic synthesis. Yeah.
Could you just say something like the real world benchmarks, where they come from? Like what kinds of programs are we?
One of these, I can. Okay, I will say something and I'll give you some names of where they came from later on. So these are extracted from real world code bases, but we have a classifier that can extract the bits of the code that can be lifted. So the actual code fragments are relatively small. As an example, some of these benchmarks come from Llama.
Oh.
Yes.
Do they include all the TenSpiler benchmarks?
Yes. Yes, I think so. Yeah, so we've got 67 real world benchmarks. We've got 10 artificial ones, which we added simply because they were challenging. They had a bunch of sort of nested parentheses in them. So our comparison points are, so TenSpiler, which is doing classic program synthesis. It is also giving you unbounded proof, which we're not. So you have to bear that in mind when you're looking at this. C2TACO, which is doing really basic enumerative synthesis, but it has some very smart heuristics. But also we were able to disable the heuristics because C2TACO is our previous paper. So we've got all of the details of it. And yeah, so we solve more benchmarks in less time. And we are also beating GPT-4, which is nice. Yeah, we do need more benchmarks though, because we are up to sort of 99% solved. So.
Just to check, so what was the GPT-4 implementation? Is it just taking samples and until you find something?
I can't remember what it's pass at, but it's like pass at 5 or pass at 10, but it's not doing any sophisticated prompting. So it's possible you could get better results with sophisticated prompting. We're essentially giving it the C program, and we're saying, please give us an einsum expression.
Got it. Thanks.
Yeah. It is maybe worth saying that we have also tried this for some classic formal synthesis problems. So this was a paper at CAV in 2024. We have a slight extension of this. So in the CAV paper, we do a slight variation on this where we can ask the LLM for more guidance as we are partway through the synthesis loop. So when we're partway through enumerating a program, we can then ask the LLM to suggest some helper functions, and we can then update the probabilistic context-free grammar based on that. But otherwise, the basic idea is very similar. Yes.
I wonder if you have done a study of this neighborhood hypothesis, where you take the outputs of the LLM and then of course you use either this your PLDI procedure or some other procedure to find a solution that works, and then metricize the distance maybe between expression graphs or some way of looking at it. Edit distance, I don't know.
So we haven't, particularly because I think it's quite hard to. So in this context, it's quite hard to say how far away the actual solution is from the guesses, because you're sort of looking at probability distributions that are sort of a gross over approximation of the actual distributions.
Sure.
You talked about edit distance, and I'm going to talk about edit distance next.
All right.
But what we haven't done is quantify our hypothesis that the LLM actually does make guesses in the right neighborhood, other than just saying, well, it seems to work.
Yeah, because I mean, A-star search is kind of using the LLM output as a starting point, but then it could end up finding a solution that may end up looking quite different, I suppose, right?
Yes.
Okay.
But it is tending to find, because it's finding solutions quickly, we know that it is tending to use the same production rules as the LLM is using, but then this is quite a coarse representation of what the LLM is doing.
So if you have the probabilistic grammar, you should be able to assign like a probability of each completion, right?
Yes.
Do we have a sense of like the description complexity in that space of like how many bits it would take to describe this program given the reference program?
How many bits it would take?
Like how likely is it to do this mutation effectively?
So no is the short answer. We're not doing mutations though. We are starting from scratch in our search, right? So the neighborhood analogy falls down slightly because we're not moving around our neighborhood. What we're actually doing is we're saying, oh, this neighborhood is full of green houses. Let's come up with a bunch of building blocks that build green houses. And then we're building lots of new programs and picking the most likely ones of that. So I guess it's not a case of how likely a mutation is, it's a case of how likely it is that you will generate that that complete program from scratch. But I agree, we still could quantify this better. I just haven't. I would be very interested if someone has strong views on how to do this though, because this is slightly not my area, how you'd actually quantify how correct our assumption is.
Fair enough, thanks.
It works on formal synthesis too. That was the TLDR of this slide. Okay, I said 2 methods, and Sanjit has slightly preempted me by asking about edit distance. So what if we could navigate the neighborhood instead of building up our programs from scratch using likely building blocks? So what we want to do is we want to be able to, our guess is here, we want to know how we change our guess to get to the solution. Navigation is easier if you have some guidance. I had a tenuous analogy here about being able to go up in a hot air balloon occasionally and sort of survey the streets and sort of come up with an estimate of how far away you are. But what I want to say is this would be easier if we could estimate how far away we were. And then as we took actions, we could then look, are we actually getting closer? Okay. I've been talking about lifting. The other insight you need once you've said, okay, what if we could estimate how far away we are? For almost all lifting problems that you care about, there is a lowering pass. Like I can't come up with a lifting problem where the lowering doesn't already exist. So you can compile TACO down to C, and then you're in at least the same language as your source program that you started with. If there isn't a lowering pass that directly maps to the lifting you want to do, there is often like maybe a series of lowering passes that takes you to some common like IR. So that might be LLVM. In this instance, I'm going to be talking about lowering to LLVM. I haven't thought about how well this would work if you have to go all the way down to like binary. I feel like that, like once you've got ones and zeros, it's probably not going to work very well. But essentially, the next bit of work that we have done is we're saying, okay, we want to lift, but let's use lowering to estimate how far away we are from our actual solution. And that gives us conrule. So the idea behind conrule is that we take a language model and guess the solution with the language model, and then we use lowering and measurement to estimate how far away we are, and then we search this space of edit rules using this measurement to estimate whether we are getting closer. The really nice thing about conrule is that I don't have to spend all of my money on OpenAI anymore. So conrule, we have a really small language model. So I think this is something like 4,000 times smaller than GPT-4. I think it's small. So Jose built this language model, and he trained this language model. One of the challenges in lifting is the availability of data. So we obviously don't have a lot of C to TACO pairs. So Jose trained this language model with artificially generated data. So he randomly generated TACO programs, and then he compiled them down to C, and he trained them with those pairs. The obvious question that someone is going to ask is, how well does this work on its own at lifting? And the answer is really not very well at all. It can solve artificially generated, like it can correctly lift artificially generated benchmarks. It can't do the real world ones at all, which was disappointing for everyone, but has led to conrule. So that's where our guess comes from, which is nice and cheap, which is nice. Yes. Yes. We're currently here. So program.
What's P? What's E hat? I think the notation here is a little.
Yeah,
confusing.
sorry, I did copy and paste this from the paper. So. Okay, so P is the input program, which is in C. E hat is the guess, which is in einsum. So this is the guess that has come from our small language model. Things that are, so we've got to here so far. We're about to go down to here, which is IRE, which is the guess, but in some lowered common representation. Yes, I'm gonna go through this step by step. So we lower with LLVM. Now what we actually need is to be able to measure the distance between, so we can lower our guess with LLVM, we can lower our original C program with LLVM. We now need to be able to estimate the distance between the two of them. What we have done in this instance is we have handwritten some syntactic distance metrics, which is not very exciting. And one of the things we want to look at in the future is, can you train a model to be these distance metrics? But we're looking at very, very simple metrics. So the difference in the number of variables in the two LLVM programs. So we can extract the loop indices from these programs, which we can do with polyhedral loop analysis. And then you can look at the edit distance between these lists of loop indices. And we can also extract like the list of operators and do the same edit distance between the two lists of operators. So yeah, they're pretty handwritten, but they are surprisingly effective and relatively simple to implement. So We're now down here. We've done some measurement and we've got some kind of similarity metrics based on the number of variables, the indices and the operators in the programs. And we want to make a choice about how we edit this program. So we have a set of edit rules which will allow us to get from any guessed program that is in valid einsum notation or valid taco, it will allow us to get to any other taco program. Like our edit rules are complete, so it's a pretty big search space. We can, however, pick which mutations we should try, which edit rules we should try to use based on our distance metrics. So in this instance, if the variable list scores badly on the similarity between variables, we will replace a variable name. Like we might then say, okay, well now the index distance metric is doing badly, so we replace the indices and so on. So we've basically got a mapping. Once you've picked which is your worst performing distance metric, we can then randomly choose which one of the edit rules we should apply from a subset of edit rules, which gives us another einsum program. So these edit rules, by the way, are being applied at the einsum, at the high-level language, not at the low-level language. So we're editing our high-level guess. And then what we will do is we will have to lower this again and repeat the process. So yeah, question.
Sorry, just to make sure I understand. So once you've generated the initial guess, do you ever come back to the LLM or you just
At the moment, we don't. One of the open questions is how do you know whether you should just discard a guess or not? At the moment, we get an initial guess and then we search the space around that guess with the edit rules and the distance metrics. I'm sure at some point you would definitely be better off saying, okay, let's have another guess. Yeah, so we repeat this iteratively until we get something which our distance metrics say is similar enough within delta, and then we can do the same testing and verification that we had before. It works. Okay, we've got more benchmarks this time. We've got 81 real-world benchmarks this time, so we definitely have all of the 10-spiler ones, and I think we have some additional ones as well. So we solve more benchmarks than classic synthesis in less time. We also solve more benchmarks than GPT-4, even though our language model is rubbish, which is very pleasing. We can also lift higher dimensionality benchmarks. I think this is because effectively a higher dimensionality program is not as far away if you've got these edit rules that sort of directly change the indexing. And we explore fewer candidates, as in the number of guesses that we explore is significantly fewer than the number of complete programs that something like C2TACO that's doing enumeration explores. This matters because for some of these programs, actually doing the IO testing is takes a decent amount of time. So, for example, Blend is spending a lot of time on IO testing, even though it's only IO testing eight programs. So the fact that the metrics allow us to reduce what we're testing really helps. Yeah.
By IO testing, you simply mean running
randomly generating inputs and running the programs.
I see.
We don't even generate that many inputs. It's literally like a handful, but it's also the compilation process as well. I motivated this by saying it would make your code go faster. It does make your code go faster. So we get a speed up of 38x on the GPU. I will say that this speed up is not, this speed up is due to lifting into a better DSL. Like we're just exploiting the DSL to get this speed up. We're exploiting the DSL and good hardware. So I could basically make these results say whatever I want.
Just out of curiosity, so presumably there are different taco programs that you could lift to, right? It's not a unique. And I'm just wondering if there's any differences in the speed ups that you might get if you were to choose different ones.
I think whilst there are different taco programs that you can lift to, they're not actually very different. Like because of the way we're searching, we're not going to find something that is like really significantly different, because so with the enumeration, you're sort of finding the shortest programs first, and with this, you're probably starting with quite a short program. Yeah, so we haven't noticed that any of this is finding, like, we haven't noticed that one technique is finding taco programs that are significantly slower than another, but that's really down to taco, not us. Yeah, so I wanted to make a bit of a comment about Oracle guided synthesis. So Sanjit has a paper where they set out a framework for Oracle guided synthesis, and there are many possible oracles in this. So your Oracle guided synthesis process is broadly that you have a learner and you have an oracle, and your learner can query the oracle and the oracle gives feedback. So CGIS is the classic example. Your query is this a solution? And the response you get is yes or no, plus a counterexample. If the answer is no, it's not a valid solution. But there are many other oracles you can have. You can have sort of membership queries. You can have sort of input-output queries. The point I want to make is that all of these oracles are semantic. They are giving semantic feedback. And most practical synthesizers are searching a space of syntax. They are searching through a grammar. So you're trying to give guidance to something that is searching a syntactic space based on semantics, which means that often the actual guidance, all the guidance is doing is, so in CGIS, what the guidance is doing is it's reducing the number of times you have to call the verifier, because you don't call the verifier until you've got a program that works for all of your counterexamples that you've seen so far. But you're not changing the enumeration strategy based on that guidance. And I want to make the claim that what we've been doing in the last 2 bits of work I've talked about is trying to bridge this gap between the semantic specification and the syntax that you're searching through. And we've been trying to come up with oracles that can give you feedback that is directly and easily applicable to your syntactic search. So in the first instance, we're using the LLM to do this, and we're hoping that the LLM can make this bridging gap between the semantic spec and the syntax that we should have. And in the second case, because we're looking specifically at lifting, we're making the observation that we can effectively, by using this lowering, we can infer a specification that would be satisfied, and then we can use that to do a syntactic comparison. But I think one of the key challenges in synthesis that I hope that LLMs can allow us to tackle is being able to bridge between the semantic specification and the syntax that you need. I'm sure Sanjit is going to tell me that I've misinterpreted the paper now. Yeah, so this was my last slide. It works. That was my point. That's all this last slide says. Are there any questions?
Thanks, very nice talk. So when you do the lowering,
yeah,
could there be something that's getting optimized out?
Yeah, so our lowering and our measurement, so our measurement is only an estimate of the distance between the two. In part, that's because, in part, that is because of the optimization. So we reduce it with the minimal amount of optimization in Clang when we do the lowering, but some stuff does get optimized away.
And does that affect, yeah. I mean, that was probably going to affect the metric, right? Because
yeah, the metrics aren't perfect. They are good enough to guide the search, but the reason why we don't wait until we found something that perfectly matches and instead we look at all programs that match within Delta is because the metrics aren't perfect, because the lowering isn't designed for this.
Yeah. So have you encountered a situation where the real program actually missed some syntactic features that was, I mean, you showed those rules and you said that you can transform from any program to any other program with those rules.
Yeah. So if the real program is missing a syntactic feature, this is where the rules help, because distance metric can detect if the real program has, for instance, missed a specific operator that needs to be included, or if it's got the dimensions wrong and it's missed some index, it's got the indexing wrong, then those our distance metric can pick up on, and then we can pick the right rules to fix it. In the first work I talked about with the PCFG, if the real program has missed some key features, all bets are off. We're not going to find, like, we're going to be very slow if the LLM has missed some specific features that are needed for the solution, because they won't be in the probability distributions.
So I guess the rules are very crucial here, right? I mean,
well, the set of edit rules is just the complete set of edit rules. They're very simple, but being able to predict which edit rule you should use is quite important.
Can I just follow on what Supratik asked? Because when you mentioned you had examples with legacy code, you don't really want to have sometimes equivalent code, but you want to have also the code that is like better version with newest features, right? Did you consider that?
That is a very good point. And the short answer is no. We're just aiming for something that behaves semantically the same and is in the target DSL. In theory, there's nothing stopping you considering that if you have some way of evaluating whether you've satisfied those criteria. You need some verifier that can check that. And ideally, you need something in your sort of measurement to detect whether you're meeting that. But yeah, we didn't actually do that.
Can you try to optimize the code for a setting where you're only interested in a subset of the input? So say I want my code to be correct, but only on stochastic matrices.
That's a very good question. I don't know. I don't know how first of all, I don't know how we would check that. That's my initial fear there. I don't know how I would write a verifier that can check whether this is correct, but only on stochastic matrices, or at least can discard counterexamples on stochastic matrices. The other thing is I don't know enough about stochastic matrices to know whether there are specific TACO programs that would be good or bad for this. So you might be reliant on selecting the DSL grammar quite carefully there.
Thanks.
In a similar vein to the earlier two questions, is the approach robust to like obfuscations in the source program? And if that's true, is there a case to be made for like pre-processing or optimizing the input program and then performing your like measure computation?
So we haven't looked at deliberately obfuscated source programs. I don't know whether I'm that motivated to look at deliberately obfuscated source programs, because I don't think you will come up with that in the wild very often. But if the distance metrics are robust to the obfuscated programs, then the approach will be robust to that. But so the distance metric that just looks at the variables that appear and that looks at the operators, those will be somewhat robust to obfuscated source code. I don't know how well the polyhedral loop analysis will cope if you end up with if you've obfuscated it by introducing more and weirder loops. Yeah. So I guess the answer is maybe not.
Okay, so in your last project, you were able to use a weaker language model.
Yes.
So my question is the counterfactual. If you had the money to run a very sophisticated large language model, do you envision improvements? And conversely, how much weaker can you damage that language model? Like, what do you really need out of it?
Okay, yes, it does get better if you have a better language model. If you use GPT-4 as the base language model, then Conrule does better than if you use the base language model. But yes, so the answer is bigger language model, better, assuming that you have the money and you want to run the money. I don't know how much worse you can make the language model, though. We didn't try to hobble it any further. I can tell you that the first technique definitely needs a better, so the PCFG technique needs a better language model than the edit distance technique. But yeah, we should look into how rubbish we can make the language model.
Right. Well, since you suggested a question on the previous slide, I will ask one. If you go back one. No, it's really more a clarification question. This last bullet here, lowering can, but only for lifting. I didn't understand that comment.
So if you want to bridge the difference, like you want to bridge the difference between your semantic spec and the syntactic difference in like the syntactic difference in your guess and your solution. This works really well for lowering because lowering means that we can. So your original specification was find a program that is the same as lowered program 1 and find a program that's the same as source program 1. What we can do because we have lowering is we can effectively infer a specification for any guess we can infer a new specification because we have this lowering. We can say, okay, this is a lowered program that is equivalent to the guess you've got. And then we can look at the difference between the two specifications effectively. This is
what you were doing in the con rule.
Yeah, and I don't know how you do that for not lifting problems. Like what you want is you want to infer a spec. So given an incorrect guess, you want to infer a spec that works for the incorrect guess and then look at the difference between them. And I don't know how to do that.
But I think your neighborhood hypothesis is actually, I mean, it applies broadly. And I think it's a hypothesis on which you can make a case for LLMs as syntactic oracles.
Yes.
Right? That is, it's a good place to provide starting points for search.
Yeah, what is currently missing for applying the neighborhood navigation approach to other general synthesis problems is how you get that measurement, which potentially is perhaps you train a model to do that measurement, and then perhaps you can do the navigation.
Yeah, that's a good point. And by the way, I think syntactic oracles also fit in the framework.
I think they do, but I don't think you mention any syntactic oracles in the paper.
Fair enough. Well, thank you for doing that. All right. Okay, one last question, and then we should go to break.
Sorry, but first, thanks for the great talk. So in the edit distance that you used, I'm wondering, so like something that shows up in earlier work is just that using the number of test cases that pass as a kind of similarity score.
Yes.
Is that something you compared to, or it didn't work, or what was the...
In this specific domain, it doesn't seem to work because basically the test cases either pass or they either all pass or they all fail. But I am aware of the symmetric work where they use the input-output examples and they look at the distance between the input-output examples that are satisfied and not satisfied. But for tensor code, it doesn't really work.
Okay, thanks.
Right, let's stand to the again. Right, so we'll reconvene at 11:15 for Osborne's talk.